Hello, welcome again. Today, we will talk about a generalization of the transportation model, denominated the transshipment problem. As I had commented, the transportation cost is the most important logistic cost, and in spite of the usefulness of the transportation models, there are certain elements not present in the problem. For instance, the warehouses or distribution centers have not been considered. The transportation model only considers the cost of direct shipments from the plants to the customers, but if a warehouse exists, this cannot be reflected in the model. Shipments between plants cannot be reflected either. Come with me to the office, and I will tell you the details. As I was saying, the transportation model only considers the possibility of direct shipments from the plants to the customers. This would be the representation as a network model. A transshipment problem is a little bit more general. The model considers the existence of warehouses. The plants will send units to the warehouses and these, in turn, will transfer the units to the customers. This diagram represents the conceptualization of the transshipment model. However, in practice there are models that could offer a greater number of options of interaction among plants, warehouses and customers. For instance, let's consider the following map. And suppose we have our plants in Node A, Node E, and Node J. And our customers are located in Node E, Node G, and Node H. Finally, let us consider that Node B, Node C, Node F, and Node I represent transshipment nodes, and that a truck could leave units for a customer, and continue its trip towards another destination. And that the routes indicated in the map could be used in both directions. Now, we only need to specify the capacities of the plants and the demands of the customers. Once we have included this information, we can start building our model. If you count the trajectories in the map, you will find that they are 15. And since each trajectory can be traveled in both directions, we will have 30 variables. Furthermore, you should note that the total capacity of our plants is 3,000 units, meanwhile the total demand of our customers is 2,700 units. Which means that our customers must receive all the quantities they request. And our plants will not use all the available capacity. Let's start with the model formulation. Define x, I, j, as the number of units to be sent from node I to node j. Therefore, our objective function will be as follows. Notice that the trajectory a, d, is found in this function. But the trajectory d, a, is also found. This means that we can send units from node A to node D, but we can also send units from node E to node A. Now, let us add the constraints beginning with the transshipment nodes, which are the easiest to represent. In a transshipment node, the units only cross it, that is, the node does not produce and it does not demand. Then, what goes into the node must leave the node. For instance, consider node B. The units coming into node B can come from node A, node C, node E, and node H. And this is represented by the variables AB, CB, EB, and HB. The sum of these variables is the total amount that comes into node B. On the other hand, the quantity this node sends is represented by the variables BA, BC, BE, and BH. And the sum of these variables is the total amount that leaves this node. Since this is a transshipment node, everything that goes in must go out. And so we arrive to the following constraint. As you can assume, the constraints for the other transshipment nodes are similar. Now, let's think about a source node. A source node is a node that has the capacity to generate units. In this case, the source nodes are node A, node E, and node J. At first glance, you may think that the units that leave node A must be less than or equal to the production capacity of node A. But if you think for a moment, this node can also receive units. And therefore, this node has the capacity to send the units it can produce, plus the units it receives from nodes B and D. The less than or equal to sign is because, as we mentioned before, our production capacity exceeds the demand. And this means that a plant may, or may not, use all its capacity. Then, the constraint for node A is as follows. As you can expect, the constraints for nodes D and J will have similar expressions. Finally, we have arrived to the destination nodes. A destination node demands units. In this case, the destination nodes are nodes E, G, and H. Here, you must think that it is possible that a unit arrives to the node, but then it continues traveling until it reaches its final destination. Therefore, the units that arrive to this node are the units demanded by the node, plus the units that are sent from this node to another node. For instance, take node E, and observe the next expression. This expression indicates that the units that come into node E, minus the units sent by the node, must be equal to its demand. The equality sign in the expression is because, given that the total production capacity is greater than the total demand, each destination node will receive the units it requests. As you can expect, the other two destination nodes have a constraint similar to the one just explained. Recall that when the constraints are entered into a computational program, all the variables must be in the left-hand side of the expression. That is the solution to the problem. I will enlarge the map to visualize the solution. Node A will produce 1,200 units and it will send everything to node B. Node B, in turn, will send 100 units to node E, and 1,100 units to node H. Node H will keep the 600 units it demands, and will send 500 units to node G. Notice that the production capacity of A is depleted, and the demand of G is satisfied. Now, node D will produce only 800 units, which will be sent to node C. And node C will transfer them to node E. Observe that with this 800 units, the demand of node E is satisfied. Finally, node J will send 700 units to node F. And node F will transfer them to node G. With this, the demand of node G is satisfied, and the production capacity of node J is depleted. The total cost of this solution will be $668,300. At the end, there is only an available capacity of 300 units in node D. But these units are the difference between the total production capacity and the total demand. As you can see, the transshipment model is very flexible, and can be used in a wide variety of cases. I hope this model will be helpful. See you soon.